In our last video, we were analyzing the sampling distribution of sample proportions. In other words, you find a proportion from your sample and you take that random sample over and over and over and over again. So for example, we were doing here the coin toss thing and how many were heads. And so we were tossing and tossing and tossing. Okay. So when we do that, we found that we could create a distribution for our sample proportions, right? Every toss of, or every set of 5 tosses was its own sample, and they had their own proportions, and we were able to create a table and a histogram and all that stuff. And that means it has its own distribution. And so we need to know, what is the theory for that distribution? What is the theorem for that distribution, if you will? And that's what the central limit theorem for proportions is about. So suppose you're going to take a sample of size n from a population with a population proportion p. Now remember in section 8.1 it was talking about means, a mu, but this one's going to be talking about a proportion p. So let's say, a certain proportion of all of America believes we need, I don't know, um, stronger gun control laws, or a certain proportion of all America believes that a Republican should be president next time, or something like that. So there's some population proportion, and you're going to draw a sample from that. Now, I wasn't picking things like gun control and presidential candidates at random. This is the theory that's going to help us analyze things like surveys. So we're going to need this theory a lot in chapter 9 and 10 and 11 and 12. All right, so we have some conditions when we take this sample. There's certain things that have to be true in order for this theorem to hold. Condition number 1, again, should not come as any great shock to anybody. We need random. We need random through this whole course. We always want everything to be random. Now, truly being random is actually kind of hard to manage, but we're just going to assume for the sake of our course that we have it. Then we need our observations to be independent of each other. So when we sample with replacement, that's not a problem, right? If you pull a card from a deck, put it back in and shuffle and then redraw, you're independent, no trouble. Take a die, take a coin, it's independent. But if you're collecting without replacement, which let's say you would be doing for a phone poll, for example. So when you call people's phone numbers, you can't call the same phone number twice. So you're doing it without replacement. That means that you want your population to be at least 20 times your sample size. In other words, you want your sample size to be less than 5% of your population size. And remember, this was discussed in 8.1. It's this equivalent of taking M&Ms out of a larger M&M bag, right? If you take a sample of size 50 or whatever out of a vat of M&Ms, yeah, you took some, but it's not going to greatly affect what's left upon this much candy stealing is made by little children. And last but not least, you need this population, or excuse me, the distribution to be normal. Now, in order to ensure that, we're going to use a little trick. Now, in 8.1, we had a different rule. It said that if it was normal to begin with, great. If not, then you need n to be bigger than 30. But here, we don't have normal distributions that way because this is for proportions. So we're going to have to ensure that n times p times 1 minus p is greater than or equal to 10 in order to make sure that our distribution is approximately normal. It's not a perfect rule of thumb, but it's the rule of thumb we're going to use for this course. All right, if we have these 3 conditions, if these 3 things are met, and remember this one in particular is different than 8.1. The other 2 were the same as in 8.1, but this condition 3 changed. In 8.1 it was 30, in 8.2 it's this n times p times 1 minus p bigger than 10 thing. If we have those 3 conditions met, then the distribution of our p hats, our sample proportions, is described as follows. So you'll have a shape that is normal. You'll have a center, right? And the center will be equal to your population proportion p. And you'll have a standard deviation of a sampling distribution of sample proportions. And that is a lot to say. So statisticians stopped calling it that and started calling it the standard error of the proportions, or standard error of p hat. Right? How far apart are the p hats from each other? And that's what your sigma p hat represents. It's the square root of p times 1 minus p over n. And that is how variable you expect your p hats to be from sample to sample to sample. All right, now our 5 coin tosses actually do not meet the necessary conditions of the central limit theorem. So what is the problem? Well, the coin tosses are random. Let me put these conditions down real quickly. And we'll see if we've met them. So we definitely had a random, yes, coin tosses are random. So, yep, we met that one, no trouble. Were they independent? Okay, well, this whole thing about the 20 times and all of that is only if your sample's collected without replacement. But that's not a problem with a coin. Coins are independent of each other, period, right? There is no replacement with a coin. So yes, we learned in actually chapter 5 that coins are independent of each other. Oh my goodness, one second. There we go. Coins have no memory, so they of course are independent of each other. So we don't have to worry about the whole, 20 times the size of the population and all that jazz. It's not relevant because this was independent to begin with. There's no without replacement here. Now where we're going to run into trouble is right down here. N times P times 1 minus P. So let's figure that out. N times P times 1 minus P. Okay, our N was 5, right? Because we were tossing the coin 5 times. N was 5, sample size right there. N equals 5. Okay, well, if that's the case and N is equal to 5, then that's the number we'll put in right here, 5. And then we want times, and then P for us, remember this is heads and tails, so 0.5, and then times parentheses 1 minus 0.5. So let me grab a calculator here. Clear it out. 5 times 0.5 times parentheses 1 minus 0.5 is 1.25. And that, my friends, is not bigger than 10. So we are in trouble, right? Because this is no good to us. It's less than 10. Or if you will, it's not greater than 10. So when you put a slash through a mathematical symbol like that, it means it's not doing what you want, right? Right? And so that's a problem for us. So therefore, we don't have normal. Right? So distribution is not necessarily normal. Because, right? And that's why our distribution became out skewed left, right? So right up here, our distribution was skewed left, not normal like we wanted. And the reason for that was because why, right? What is happening here that is causing our problems? And the answer is, well, it's the sample size, right? If we wanted to ensure that it would be normal, then we need to take a bigger sample size. Actually, I'm going to unbold these to make it more obvious what the answers are right here. Okay. All right, so in order to ensure that we would meet condition 3, we should take a bigger sample size. To fix this, we would need to take a larger sample size than 5. In other words, we'd have to toss the coin more. Which is, I believe, yeah, how could this be changed? That's how you could change it, right? So to fix it, to change it, you need to have a larger sample size. But that brings up the question on its own of how large a sample size do we need? So let's figure that out. And that's the next example right here. So what would be the minimum number of coins, right? 5 coins or 5 tosses, because it kind of doesn't matter with coins. If they're coins, you can either toss 5 separate coins or take one coin and toss it 5 times, right? Tomato, tomato, right? And it's because they're independent that it doesn't matter. That's why, right? Okay, so what is the minimum number of coins that must be tossed to ensure that it's normal, roughly, right? I think that's ensure, I-N, instead of ensure. Sorry about that. I always get those two confused. Okay, so this question is asking, look, you want this to be greater than 10, right? You want n times p times 1 minus p to be bigger than 10. So we want n times 0.5 times 1 minus 0.5 to be bigger than 10. Okay, so what we need to do is figure out what the heck is 0.5 times 1 minus 0.5. So let me grab a calculator. Yes, I do know what it is off the top of my head, but I want to make students that don't know it off the top of their heads understand where it comes from. So it's 0.25. So n times 0.25 is greater than 10. Now, the way inequalities work is you treat them just like equation signs. You treat this symbol right here like it's an equal sign. and you divide both sides by the same value. So I'm going to divide by 0.25. And the reason I'm doing that is because 0.25s will divide away to 1, right? 0.25 over 0.25 will cancel out, if you will, and just leave you the n. But of course, with an equation in algebra, you've got to do whatever you do to the right-hand side to the left-hand side, or vice versa in this case. So I need n to be greater than or equal to whatever the heck this number is. I believe it's going to be 40, but let's double check. 10 divided by 0.25, and it's 40. So here we go, 40. And there you have it. Now we're going to get a little bit more involved into calculations like this in chapter 9, but for right now this will do, right? So to ensure the minimum sample size required to ensure normality, you use the same idea up here as the top equation right here. So you're going to have to use that inequality. Actually, it's not an equation, it's an inequality. So you'll have to use that inequality. You'll have to substitute in the parts that you do know, the p and the 1 minus p, and then solve it for n. So now for example 2, let's do something very different. Let's consider a 4-sided die, and you're concerned with p hat, which is the sample proportion of 3s. The graph below illustrates 2 sampling distributions for p hat, one where n was 100 and one where n was 1,000. And we're supposed to label each distribution with the appropriate sample size, the center, and the standard error. Well, they're not asking for much, are they? All right, so let's see here. First of all, they're going to be both normal because our n is quite large for both of these cases. So we can see the shape is normal, that's fine. Center and spread are where we're going to be interested in. So the center is going to be p, and then our standard error is sigma p hat, or SE of p hat, which is the square root of p times 1 minus p over n. So we need to figure out which one's which. Oops, hold on. There we go. Okay, so let's look at it just a little bit. All right, let's start with n equal to 100. Now the center is the mean of the p hats, which is going to be mu sub p hat, which is 0.25, because that's your p value. Let me put that in there, right there. And now where am I getting that from? Well, it's p, which is your proportion of success, which would be 1 out of 4 because it's a 4-sided die, which is 0.25. Let me just pull up a picture for you real quick. A 4-sided die looks like, well, there's a couple basic types. One's where the numbers are on the bottom, one's where the numbers are on the top. There you go. Just a little Google image search. So here's one that rolled a 4 because the 4 is on the top. Here are the other kinds where the 4 is on the bottom, right? So that rolled a 4. This one over here rolled a 3. So there's 4 sides on a 4-sided die. So the chances of rolling, I believe we're interested in a 3, is 1 out of 4, right? 0.25. Okay, yeah, 'cause we're interested in the proportion of 3s. Okay, so now that's the center. The standard error is your spread. Okay, so we have to write that formula, which is the big sigma p hat equals square root of p times 1 minus p over n. So let me type that up 1 second. There we have it. So the standard error of the p hat is the square root of 0.25 times 1 minus 0.25 over 100. All right, well, that's going to be kind of complicated. Let's see here. Square root 0.25 parentheses 1 minus 0.25, close that parentheses, divide it by 100. You have to make sure that everything you're typing is underneath that square root because the whole fraction is under the square root. So you want to see that little square root bar extending over your 100. And then you press enter. And you get 0.0433. I'm going to write that. And actually for these ones, I like to do about 6 decimal places because you can lose accuracy real fast with proportions. All right. Now, for n equals 1,000, it's the same thing. The only thing that's different is your spread, right? Your spread won't be that large because your denominator will be 1,000 instead of 100. So let me type this in. There, I've got all that typed up. Now let me go find the same thing I just typed, but I'm going to do it but with 1,000 in my denominator. So 0.25 parentheses 1 minus 0.25 close parentheses divided by 1,000. enter. And I get 0.013693. There, and now I labeled those values on the graph so you can see. The tall, skinny ones with 1,000, and the shorter, kind of more spread out one is 100. And that's because it has a larger spread. The spread for the gray one is 0.04, whereas the spread for the black one is 0.0137, roughly, right? And remember to keep about 6 decimal places for these standard errors because since everything is a decimal, because proportions are always less than 1, you can lose accuracy real fast if you round too much. So let's make a note right there. Keep 6 decimal places for standard error of p hat. There we have it, right there. All right, we're done with those 2 examples.